everyone, my name is Bacelar. I'm a PhD candidate at Auburn University, and I'm here to present on this meta-analysis that investigates the effect of enhanced expectancies on motor learning. This study was led by me and Juliana Parma in collaboration with William Mura and Matthew Miller. According to the optimal theory of motor learning, practice conditions wherein one's expectancies for future positive outcomes are enhanced lead learners to focus on a task goal, which enhances motor performance and learning. In the literature, drift manipulations have been used to enhance learners' expectancies for future success, such as providing learners with positive feedback and social comparative feedback, implementing self-modeling strategies, influencing one's perception of task difficulty and conceptions of ability, and providing extrinsic rewards. The goal of the present meta-analysis was to investigate the effect of enhanced expectancies on motor learning. As a secondary goal, we aim to estimate the effect of each one of these manipulations on motor learning. From May 30th until June 19th, 2020, the databases PubMed, PsycInfo, and Web of Science were systematically searched using a combination of keywords that varied according to the intervention of interest. Studies published in English or Portuguese were considered eligible if they met the following inclusion criteria. It was published in a peer-reviewed journal, it had an experimental design, it included at least a positive enhanced expectancies group and a control group, or a diminished expectancies group. It used a task requiring movement to accomplish a goal that's increasingly likely to be achieved with practice. It included at least one delayed retention test, and finally, it assessed an objective behavioral measure. Studies were excluded if they failed to meet the inclusion criteria and or had insufficient data. Out of the 125 studies fully screened for eligibility, 48 were included in the meta-analysis. To investigate the effects of enhanced expectancies on motor learning, we focus on the comparison between enhanced expectancies and control groups. The main variable of interest was performance on a delayed retention test, defined as the test performed at least 24 hours after the end of the acquisition phase. Out of the 48 studies included in the meta-analysis, we were able to compute 56 effects, specifically Hedges G. Before estimating the overall effect of enhanced expectancies on motor learning, funnel plot, visual inspection, and measures of influence statistic were used to identify outliers in our data. 2 studies were identified as outliers and removed from the subsequent analysis. The remaining 54 effect sizes were fitted into a random effects model to estimate the overall effect size of interest. Results reveal an overall effect size of medium magnitude, indicating a positive effect of enhanced expectancies on motor learning. Next, we proceeded to assess the presence of reporting bias and or inflated effects in small studies. Funnel plot visual inspection indicated asymmetry, even after outlier removal, which was confirmed by the results of the Agres regression test. To address our secondary aim, we carried out a moderator analysis to investigate the effect of enhanced expectancies on motor learning as a function of the type of manipulation. Results reveal a large effect of positive feedback on motor learning. We also found a medium effect of social comparative feedback and a small effect of perceived task difficulty and conceptions of ability. There was no evidence that extrinsic rewards and self-modeling improve motor learning, but few studies implemented these manipulations, precluding reliable estimates of their effects. Finally, we conducted a second moderator analysis to identify the effects of enhanced expectancies as a function of the different types of comparison groups adopted. We observed a small effect when comparing enhanced expectancies to control, and a medium effect when comparing enhanced expectancies to diminished expectancies. However, the effect of enhanced expectancies was not significantly influenced by comparison group. To our knowledge, this meta-analysis is the first quantitative synthesis of the growing body of studies indicating enhanced expectancies facilitate motor learning. Based on the results, enhanced expectancies has a medium-sized benefit on motor learning irrespective of comparison group, which is in line with the optimal theory of motor learning. Different methods of enhancing expectancies have distinct effects, with positive feedback showing a large effect, social comparative feedback showing a medium effect, and perceived task difficulty and conceptions of ability showing a small effect. We do not find evidence that manipulating extrinsic rewards or self-modeling affect motor learning. Thus, we recommend future research investigate these manipulations, in addition to conceptions of ability, since only 7 studies implemented this manipulation. The present meta-analysis also reviewed evidence of reporting bias in underpowered studies indicated by a median sample size of 14 subjects per study, which likely caused the overall effect size to be overestimated. Therefore, to estimate the effect of enhancing learning's expectancies on motor learning more accurately, we recommend researchers conduct pre-registered studies and register reports with a priori sample size calculations. Researchers conducting a priori sample size calculations should consider these meta-analysis effect sizes to be overestimated and are encouraged to power their studies to detect effects close to the lower bound of the 95% confidence interval. Thank you very much for watching this presentation, and please let me know if you have any questions.